Welcome to lecture 49. In this week, we are talking about constant nonlinear programming. As of now, we have discussed three different methods to solve a general nonlinear programming problem with constants. The first one we talked about was successive linear programming. So, what we did is, given a nonlinear programming problem, we successively used linearized version of that nonlinear programming problem, and then we could make use of linear programming technique to solve the problem. Next, we talked about successive quadratic approximation of a nonlinear programming problem. So, there given a nonlinear programming problem, we successively approximated it by a quadratic programming problem, where the objective function was a quadratic function and all the constants were linear, and we could solve it efficiently using techniques of solution of quadratic programming problems. Then we talked about penalty function method, which is a transformation method, and this transformation methods converts the original constant nonlinear programming problem to a sequence of unconstrained optimization problem. So, the unconstrained optimization problem can be efficiently solved by several powerful optimization algorithms that are available. So, today we will talk about another transformation method, which is known as augmented Lagrange multiplier method. So, this method also transforms the general constant nonlinear programming problem to an unconstant function, which can then be solved using unconstant optimization techniques. So, in this lecture, we will see how we convert or transform a general nonlinear programming problem to an unconstant problem using augmented Lagrange multiplier method. So, this is what we just talked about. The penalty function method and augmented Lagrangian multiplier method are called transformation methods, as these methods transform the original constant problem to a sequence of unconstant problems. The motivation is that we can solve the unconstant optimization problem using algorithms for unconstant problems, which can be solved efficiently and reliably. Now, we have talked about two different types of penalty function methods, exterior point method and interior point method. So, let us talk about some features of exterior point method. The exterior point method is applicable to both equality and inequality constant problems. The starting point can be infeasible. The exterior point method iterates through the infeasible region. In this infeasible region, the objective function may not be defined, and also the constant functions in this infeasible region may not be defined. So, objective function and constant function may or may not be defined in this infeasible region. If the iterative process terminates prematurely, the final point may not be feasible and hence may not be usable. Now, let us look at some of the features that we have encountered with while talking about interior point method. Interior point methods only applicable to inequality constant problems. The starting point must be feasible. Interior point method iterates through the feasible region. If the iterative process terminates prematurely, the final point will be feasible and hence may be usable. So, what are the weakness of the penalty function methods that we have noted? The penalty function method tend to be ill behaved near the boundary of the feasible set, and near the boundary of the feasible set, the optimal point usually lie. So, the penalty function method, as it approaches optimum point, the method tend to become ill behaved. The choice of the penalty parameter r at successive steps is not easy. Bad choice of parameter r can seriously affect the computational effort. With increased value of the penalty parameter r, the Hessian matrix of the transformed unconstant function becomes ill-defined as r tends to infinity. We have seen that for exterior method, we start with a smaller value of r and go on increasing the value of r at each successive steps. But as we do that with increased value of r, as the r goes to infinity, the Hessian matrix of the unconstant function becomes ill-defined. So, augmented Lagrangian multiplier method was introduced to alleviate some of these problems. In this method, there is no need for the penalty parameter r to go to infinity. So, the problem of r going to infinity and that causing ill-defined Hessian matrix of the constant function can be alleviated. The augmented Lagrange multipliers method combines both Lagrange multipliers and penalty function methods. So, the augmented Lagrange multiplier method combines both Lagrange multipliers and penalty function method. So, we are familiar with both the methods now. So, it will be easy for us to understand the augmented Lagrangian multiplier method. So, first let us discuss augmented Lagrangian multiplier method as applicable to a constant problem with only equality constants. So, we first consider a nonlinear programming problem with only equality constants. So, we have minimizing an objective function f x, x is n vector and subject to m equality constants. So, you can easily formulate the Lagrangian function for the equality constant problem. All we do is we define Lagrange multiplier for each equality constants. So, if you have m number of equality constants, we will take lambda 1, lambda 2, lambda 3 up to lambda m as Lagrange multipliers. Then multiply each equality constant with its corresponding Lagrange multiplier and sum them up and add this sum to the objective function. So, that gives me the Lagrangian. So, we are familiar with this Lagrangian formulation. So, now the augmented Lagrangian function is defined by using exterior penalty function approach to define the new objective function. So, note that the augmented Lagrangian function is nothing but the Lagrangian function plus the penalty term. So, note that we have added the penalty term for the equality constants. So, we have used the parabolic penalty term that we have discussed in previous class and this is an exterior penalty function. So, the augmented Lagrangian function is defined by using exterior penalty function approach to define a new objective function. So, the Lagrangian function, which is a function of the decision variables and the Lagrange multiplier is lambda, we add the penalty term to this Lagrangian to obtain augmented Lagrangian function. So, this part is the usual Lagrangian function and I have added the penalty term, which is the parabolic exterior penalty term here to the Lagrangian to obtain the augmented Lagrangian. Now, look at this augmented Lagrangian function. R is the penalty parameter. So, if the penalty parameter R is 0, then this term vanishes and what you obtain is nothing but the Lagrangian. Similarly, if all the eigenvalues, all the Lagrangian multipliers lambda 1, lambda 2 up to lambda m all are 0, then this part vanishes and what remains is nothing but the classical penalty function that we have seen in our previous class. So, you understand clearly that the augmented Lagrangian function is Lagrangian function plus the penalty term. So, if the penalty term vanishes, what remains is the Lagrangian, and if the Lagrangian multipliers become 0, what remains is the classical penalty function. So, this augmented Lagrangian function needs to be solved, and solution to this augmented Lagrangian function will lead to the solution of the original constant nonlinear programming problem. So, if the Lagrange multipliers are fixed at their optimum values, the minimization of the augmented Lagrangian function gives the solution of the original constant problem in one step for any value of the Lagrangian multiplier R, penalty parameter R. So, I repeat, once I have formulated the Lagrangian function, the optimization of the Lagrangian function will lead to the optimization of the original constant nonlinear programming problem. If the Lagrange multipliers are fixed at their optimum values, the minimization of the augmented Lagrangian function gives the solution, that means the minimum point for the original constraint nonlinear programming problem in one step for any value of the penalty parameter R. In that case, there is no need to minimize the function, that means the Lagrangian augmented Lagrangian function for an increasing sequence of values of the penalty parameter R. Since the values of Lagrange multipliers are not known in advance, an iterative scheme is used to find the solution of the problem. In the first iteration, the values of Lagrange multipliers are chosen as 0, the value of the penalty parameter R is set equal to an arbitrary constant, and the function, that means the augmented Lagrangian function, is minimized with respect to decision variables x to find the optimum value of the decision variables. The values of the Lagrange multiplier and the penalty parameter are then updated to start the next iteration. So, this is how we can update the Lagrange multipliers, where k denotes the steps or the iterations. So, x k is the starting vector used in the minimization of augmented Lagrangian function. So, this expression gives me an update rule for the Lagrange multipliers lambda. Similarly, the penalty parameter R can be updated as R k plus 1 equal to C into R k. So, penalty parameter at k plus 1 step becomes a multiple of penalty parameter at kth step. So, C is that multiplier and C is greater than 1. So, now let us talk about the augmented Lagrangian multiplier method for inequality constants. So, that means we are now considering an optimization problem which has only inequality constants. So, I have to minimize the function f x which has x as n vector subject to p number of inequality constants. All inequality constants are less or equal to type. We have seen how to convert a less or equal to type inequality constant to an equality constant by adding slack variables. So, we can convert a less or equal to type inequality constant such as g of x less or equal to 0 can be converted to equality constant by adding a non-negative slack variables sigma square. So, we can formulate the Lagrangian function. So, to formulate the Lagrangian function, you first convert the inequality constants which are all less or equal to type to equality constant by adding a non-negative slack variables sigma j square to each inequality constants, and then for each converted equality constants we define Lagrange multiplier and then take their product, sum them up and then add to the objective function f x. So, you have the Lagrangian function. So, similarly augmented Lagrangian function can also be now formed simply by adding the penalty term. So, we have now this converted equality constants. So, you can make use of the parabolic penalty term. So, you have the penalty parameter r and you have the parabolic penalty term. So, this gives me the augmented Lagrangian function. So, you have to minimize this augmented Lagrangian function to find out the minimum of the original constant nonlinear programming problem. So, there are various unconstant minimization problem, and you can note that the augmented Lagrangian function is nothing but an unconstant function which can be minimized using an unconstant optimization algorithm, and that will give me the solution of the original nonlinear programming problem. Now, this form for the augmented Lagrangian function is basically equivalent to a simpler looking form as shown, where we are defining a new term alpha which has the definition as shown. So, again you follow the similar update rules for the Lagrange multiplier at each steps. So, now if we combine these two strategies for handling inequality and equality constants, I will be able to handle any constant nonlinear programming problem with both equality and inequality constants. So, suppose now we have this nonlinear programming problem where I have to minimize an objective function f x which has n decision variables. There are p inequality constants and there are m equality constants. All the objective function and constants may be nonlinear function of the decision variables. So, first by combining the augmented Lagrangian function for inequality constants and equality constants, I formulate the augmented Lagrangian function for this general problem. And then this augmented Lagrangian function has to be solved using an unconstant optimization problem, unconstant optimization algorithm to obtain the optimal solution, here minimum point for this general nonlinear programming problem. Here the update rules for the Lagrange multipliers are as shown. Note that there are a set of Lagrange multipliers associated with the original equality constants and there are another set of Lagrange multipliers which are associated with the inequality constants. So, we have these update rules for the Lagrange multipliers as shown. So, what we saw is the augmented Lagrangian function for problems with only equality constants, problems with only inequality constants and problems where both equality and equality constants are present. Once you can formulate the augmented Lagrangian function, we can make use of any unconstant optimization algorithm to find the minimum of the augmented Lagrangian function. So, the minimum of the augmented Lagrangian function will give me the minimum of the original constraint problems. So, with this we will stop our lecture 49 here, but before that we will talk about some advantages for the augmented Lagrangian multiplier method. The value of the penalty parameter r need not be increased to infinity for convergence. The starting vector need not be feasible. It is possible to achieve g x equal to 0 and h x equal to 0 precisely and non-zero values of the Lagrange multipliers for the active constants. So, that means the exact constant satisfaction is possible. So, the main advantages are that the penalty parameter r need not be increased to infinity for convergence, the starting point need not be feasible and exact constant satisfaction is possible. So, with this we would like to stop lecture 49 here.